Anomalous diffusion is a diffusion process with a non-linear relationship to time, in contrast to a typical diffusion process, in which the mean square displacement, sigma r2, of a particle is a linear function of time. Physically, the MSD can be considered the amount of space the particle has explored in the system as here. Unlike typical diffusion, anomalous diffusion is described by a power law, R2 dt, where d is the diffusion coefficient and t is the elapsed time. In a typical diffusion process, alpha equals 1. If alpha greater than 1, the phenomenon is called superdiffusion. Superdiffusion can be the result of active cellular transport processes. If alpha less than 1, the particle undergoes subdiffusion. The role of anomalous diffusion has received attention within the literature to describe many physical scenarios, most prominently within crowded systems. For example, protein diffusion within cells, or diffusion through porous media. Subdiffusion has been proposed as a measure of macromolecular crowding in the cytoplasm as here recently. Anomalous diffusion was found in several systems including ultra-cold atoms, telomeres in the nucleus of cells, in single particle movements in cytoplasm, and in worm-like micellar solutions. Anomalous diffusion was also found in other biological systems, including heartbeat intervals and DNA sequences. The daily fluctuations of climate variables such as temperature can be regarded as steps of a random walk or diffusion and have been found to be anomalous. In 1926, using weather balloons, Lewis Richardson demonstrated that the atmosphere exhibits superdiffusion. In a bounded system, the mixing length is given by the von-Karman constant according to the equation Lm equals kappa z displaystyle L underscore m equals kappa z, where L m displaystyle L underscore m is the mixing length, kappa displaystyle kappa is the von-Karman constant, and z displaystyle z is the distance to the nearest boundary. Because the scale of motions in the atmosphere is not limited, as in rivers or the subsurface, a plume continues to experience ladder mixing motions as it increases in size, which also increases its diffusivity, resulting in superdiffusion.